Thanks for inviting me to present to the community. I'm Din Fan. I'm one of the founding engineers in Alluxio, and right now I'm running the open source initiative in the company, but also I am the PMC co-chair for the open source Alluxio project. So today, I want to talk about the history and also the overview for Alluxio open source, and dive a little bit into the technical side, talking about what problems we're solving and how people are using this open source technology to build their heterogeneous data platforms. This is about me, my email. Before I joined Alluxio, I was working on building next generation large scale storage system in Google, and prior to that, I am a Ph.D. student in Carnegie Mellon, also working on a similar space, working on distributed system, building storage systems. A little bit about Alluxio this was originally a research project used to be called Taikan in UC Berkeley AMPLab. At that time, the project was led by then the PhD student called Haoyun Li. He is right now the founder CEO for the company. And we are backed by the top VCs, including Andreessen Horowitz. And totally, we have raised 17 million. We announced the Series C of $50 million last year. We are deployed in the production. The open source technology has been deployed in production at large scale in Facebook, Uber, Microsoft, Tencent, TikTok, and many other giant, like many good, very famous companies. They're using this technology to build their platform and solving their I/O issues. We today have more than 1,200 contributors on GitHub. In last year, there's some we did some statistics. More than 40% of the contribution on GitHub were contributed by our community users. So this is a very active community, and we work with our community hand in hand to help them in case they have any issues, they want to fix anything. So in 2020, I think there's a open source there's some project initiated by Google and OpenSSF to evaluate different open source projects on GitHub. And our project was ranked as the 9th most critical Java-based open source project. I want time travel to about 7 years ago, when this was still a incubation. This was still a project incubation in UC Berkeley AMPLab, and this is actually slides I took from the retreat in 2015 in the AMPLab. At that time, the project was still called Taikan, as we're talking about how we can solve an issue, for example, especially issues for Spark. If you are familiar with Apache Spark, this is a very powerful, very popular tool to process data, especially big data. So at that time, Apache Spark was also incubated and created and incubated from UC Berkeley AMPLab, and that time was really talking about how can we use memory in memory to process data, to do the computation. So that actually is very fast, very advanced technology, but on the other side, people are criticizing in the way like, oh, memory is still very expensive. How can we first make this memory usage more efficient, and second, how can we make sure the job is more reliable, because at that time Spark was still very young and there's a lot of issues that people are still seeing. Yeah, so that was the context when Taikan was created, was more like a sister project for Apache Spark and helping Spark solving different issues. I listed some like in the beginning in 2012. This project was created in December 2012. I think that's actually around Christmas vacation. And later on, we see more and more contributors joining. Like this is listed to in 2015, we have more than 70 contributors. But today, remember, the number is 1,200. So over the past 7 years, we see a tremendous growth in the participants of this open source project. Okay, so in 2015, the problem we are solving in the data ecosystem is to enable memory speed, data sharing across different computation frameworks. It's more like Spark. It's more emphasizing on Spark. So this is why all different Spark jobs, they're using memory extensively, very hungry, so they can store their RDDs. They put all the RDD, internally there's a data structure called RDD. There's a component called RDD that is put in memory. So Spark jobs is pretty hungry in using memory. And then at that time, Tachyon was proposed to, how about let's share the RDDs across different Spark jobs so we can have memory usage consolidated rather than each single jobs using their own resource to store the same, perhaps the same RDD across different nodes. So in that way, we can save more memory, and also in this way we can checkpoint the data, the RDD, the data structure into Tachyon, so you can avoid, in a case like your job crashed, you don't need to start from scratch, right? You can just start from where you checkpointed to Tachyon at that time. So that's the problem we're solving in the data ecosystem in 2015. But today it's 2022. The ecosystem landscape for this ecosystem has been evolved tremendously. So I'm listing a bunch of different things that we are observing as in the big data ecosystem. So for example, at that time we see a lot of on-premise Hadoop deployment. But right now we see more and more cloud-based deployment. On the tooling side, in 2015, if you are solving big data problems, likely you're using either MapReduce, I use MR to stands for MapReduce, or Spark, which is still young at that time. And today, if you're solving big data analytics or AI problems, you see a bunch of different tools you can choose, like Spark, Presto or Trino, Hive, Tensorflow or PyTorch for AI problems. And these frameworks are getting more mature and much better compared to 5 or 7 years ago. So for example, like in the early days, we see, because a lot of these are written in Java, you see a lot of OOM issue, but right now they are much more stable. And also we see the data access becomes very different compared to 7 or 8 years ago. At that time, not too many different ways to use the data, and most of the cases you just sequentially read. Sometimes we call this as scanning this data, which is the unstructured file. When I say unstructured, that pretty much means these files are the content in these files, the data of this file in these files is arranged or recorded in a way like, this is one line, the next line. So that's the way you consume the data in the file. Typically log files recording how people are using your service. But today, this situation has been changed a lot. Especially people are coming up with a smart way to store the data. They call this either structured data or more specifically like columnar data, which means, I understand the schema of the data, so I save the data column by column. If you think you are actually dealing with a table, this is more popular, especially more popular in a way you are dealing with the SQL analytics. So you're essentially saving a table. Then instead of saving the data row by row, line by line, you do this column by column. So in this way, it enables much faster data access or much faster way to query the data in this table. So that is the change that has been changed dramatically in the past few years. And also, early days, the big data ecosystem is more designed to store maybe much bigger files. So when I say bigger, it means like on the order of hundreds of megabytes, or sometimes gigabytes, or even like terabytes. This level of bigger files. And the reason for that is because at that time the storage system was not designed or cannot do a good job to handle many small files. So people are consolidating consolidating a lot of small files into bigger files to avoid overloading this different the storage systems. But today, because the AI ML workloads, especially people are training their models using a lot of small pictures or video clips, so we see it's more and more common, like people are saying, oh, actually, for my training job, I want to handle millions of small files. Last week, actually, I'm having a conversation with a advanced company in the payment industry, and they told us their goal is actually to train the model with billions of files. Billions, that's thousands of millions of files. That's a really huge model. So that's the level, the scale people are talking about today. So essentially, the data is different. Previously, it's unstructured, it's row by row. Now it's a columnar, and that means like it's more ad hoc, random reads into this columnar data because they know where to access. And also, number of files becomes different. The size of files are also the range of file size is much bigger now. Another interesting observation is we're seeing the storage service, if you're talking about the big data, is changing quite a lot. So it used to be the case if you want to store a huge amount of data with commodity hardware, HDFS is perhaps the only choice for you. But today, with the so popular, the increasingly more popular cloud service, especially in the public cloud, S3 and other, we call this object storage system, becomes much more popular. And HDFS is still in service, but they are more or less as a legacy storage right now. And one of the reasons is deploying HDFS, maintaining HDFS is a never easy job. It can take a team months or weeks or months to deploy your HDF, to maintain and stabilize your HDFS and fine-tune the service. With this public cloud service, it's so easy. You just need to input your credit card information. You can finish the registration, open account in 5 minutes, and then you get a service running. And it's so easy right now to get, I want to have this service in the US East, or I want to have my service in US West because that's where I'm using this service. And so basically choosing different region to serve, to buy your service is also super easy. It's part of this 5 minutes process to buy the service. Yeah, so that means it's very easy to get a service like this, to store a large amount of data. And also it's very easy to choose which region you want to run this, or which region you want to optimize the performance for. Least but not the last, we see the resource and job orchestration framework has been evolving. And used to be the case, Yarn is the popular or maybe dominating framework, but now everyone is talking about Kubernetes. It's like a no-brainer. Like everyone believes Kubernetes is the future way, and this is basically how you are running many machines, many computation machines, or large pool of computation resource as a single place that Kubernetes can provide you the easiness of maintenance and also monitoring on all these different good things as just running a single lab, just as you're just running a laptop as a single node. So all these are changing. The evolution is huge from Hadoop era to the cloud native era. So essentially, we're seeing there are a few things driving this evolution. One is the data is generated more and more, and because it's so easy to create a service, we see the data silos. To solve this problem, we see different companies are doing the data copies from time to time. They can have data silos because of legacy reasons, or because they have a topology reason, like they want to optimize the service for one region or in a different other region. So, and that means, which is good, like, but that also means you have to maintain the consistency, the data consistency. Sometimes people use copy, sometimes they use a synchronization tool to make the data platform more complex. And also because the more products are built in a data-driven way, and more product teams are using the data to guide their business insights, to guide their decisions. So, and they're just, people are inventing more and more ways to use the data to get the insights, right? So that means you have to use different way to access the data, because a lot of different tools are built with different assumption. Like some tools are maybe built with a legacy code, so they assume, oh, this is more like a code in the data is more like something sitting in your own laptop or on your own server. Or sometimes this is, oh, this is a very cool new tool in Node, understands S3 is the most interesting way most popular way to use data. Now I know how to access data on S3. So basically, there can be multiple different ways you need to support to integrate with your data. And also another driving force we see is the new computation engines and also new storage engine is coming out is constantly coming out. And we see the tech trend is like a new wave of new cycle to the life cycle for a new computation and storage technology to be invented is like every 3 to 8 years, and people are talking about a whole new wave of different ways to do your applications or to save your data. So that means we are seeing a mix of technologies in different from different times, like where people still running their applications on premise, or they're talking about in cloud, fully embracing the cloud, or sometimes the hybrid mode of this, or even more advanced. They want to get more negotiation power, so they want to enable multi-cloud choices to keep their cost lower. So all these different environments and different properties, you need to, like people are seeing this as a part of the complexity for their data platform. So I typically use this as an example, like for example, a lot of companies start from one single box like this. They start with a single Hadoop cluster with Hive, a Spark, a Presto, and then they start to run different other applications doing machine learning, and then they exploring the AI and ML workloads, or sometimes the cloud services. So they embrace the AWS, sometimes like just for one example. And later on, they found, oh, I want to keep two choices because I want to keep my potential. I want to still keep my potential choice open. I don't want to be locked in one single choice of the cloud provider. So they also need to support data, like for example, Google Cloud. And this is a very complicated diagram. This is very busy. So and it creates a lot of trouble for engineers to support. I want to run all this in different environments. So that's where we're seeing a strong demand for simplification. People are talking about how can we serve analytics and AI from different multiple data locations with a unification way, with a unified way to consume the data there for both workloads in analytics or AI. And people are also talking about how can we automate this, like without manually building this infrastructure or tools to migrate data from one location to another, or keep the data in two different locations in sync. And this is efficient access and also data management part. Third, the simplification people are talking about simplification because they want to maintain a single stack. This is my stack of data. I want to run my code, my applications. I just maintain one branch of this application, but I want this application to be able to run in my own on-premise data warehouse, or on AWS, or on Google Cloud without changing, or at least without changing too much into the configuration, into the code. Ideally, not changing the code at all. So this will enable a smaller team to support much bigger scope of the computation in a hybrid or multi-cloud environment. So that's why we're building this open source technology called Alluxio. As I mentioned, like it used to be the case, this is a sister project for solving particular issues we see for one particular computation engine. But now this is what we're really solving. It's adding a new layer in this data stack. We want to provide a unification from different storage, from different data sources, and provide different ways to consume this data for different applications. Now we're only talking about big data analytics or AI, machine learning AI workloads, not talking about, like, for example, traditional transactional database or some other like a standard like a Unix workloads. So that's where we are focusing right now, and we're building this layer for these workloads we're targeting. So the previous complicated diagram can be simplified using this Alluxio approach. So we're building this logical abstraction, and you can think this is a virtual data layer for different applications running in different environments, AWS or GCE, or in on-premise Hadoop warehouse or some other satellite cluster. So they are just accessing a virtual data layer. So they don't need to handle the data migration. They don't need to handle how to connecting data, configure data from applications perspective. I'm just facing a logical namespace. That system called Alluxio is responsible for fetching the data for me without me worrying, oh, should I copy the data? Should I handling data consistency? All this complicated or manual and error-prone stuff. So I want to pause here and see whether there's any questions from the audience. I do see some questions here. Actually, this is from Case. What is considered small? For example, smaller than 1 megabyte. Yes, smaller than 1 megabyte in the big data world is considered as a small. And especially we have seen a lot of cases there. People are just storing or dumping files with 100 kilobytes or 200 kilobytes, typically files of photos, and especially for machine learning and AI workloads. And that is considered as a very small and very, in a way, adversarial to storage system. It's always a pain point. Serving many small files in that range is always the hardest workload to handle. Any other questions about the context, about the for example, the space we're talking about? Yeah, this is a very brief review about this open source project. Started with UC Berkeley AMPLab in 2014 with 1,200 contributors, 9,000 Slack members. I'm always on Slack, by the way. If you have any question, join our Slack to have conversation with me. Yeah. So today, instead of having Alluxio just solving this, like in the old days, just like a Taikan to solve a particular problem for one particular application, we're now adopted by many different companies solving their I/O or data virtualization issues. And you can see the big logos from different sectors, from internet to e-commerce to cloud providers or telco, including also financial services. Yeah, different sectors are using this to solve their data ecosystem, to solve their data challenges. So I want to give a very quick study about how people are running this. This is one of the top travel platform, and they want to build a unified data lake across different geo in AWS. They have many different products run by different teams across the world, actually. Yeah, and this is partly because the nature of running this is a big corporation and part of the nature of a lot of acquisition. So, so long story short, they're running different data stacks in different parts of the cloud. And what they're facing is they need to, today they want to have this centralized data lake, one in one region for data analytics, to enable their data scientists to query data across different regions, across different data stacks. So a challenge they're facing is they have to migrate the data. They have to copy the data from different locations to consolidate it into this central data lake, which is very error prone and also slow, costly, but also providing creating data inconsistency problem. Like if you run job in, for example, in this US West 1, you see one result, but before the most up-to-date data is migrated to here, to the central data lake, you may see inconsistent results running a query in here, which is bad. Like they get complained a lot about this. So instead, having this data migration process manually and also costly, they're adding this virtualization layer called Alluxio in here to represent the data on the remote data center, in the remote regions. So we have the mechanism internally to bound the data staleness to freshness, and also to provide efficiency. For example, if the table is requested from analytics here repeatedly, then we have a way to tell, oh, this is a hot data, and we can migrate data to we can cache the data here. So in the centralized data lake. So in next time when you access the same data, you don't have to go there, check the data again. So all this data migration and the consistency handling is handled by us. And in this case, they can just unify the data silos. They appear just like the local data to their in this centralized data lake. So they don't need to manually running any application to move the data, but also enhance their user experience with consistent high performance and reducing the time to insights. And more importantly, they can avoid copying end user data at all. Like we have the intelligence to tell which data is more used and which data is not used at all. So we don't need to migrate the data. So they see 50% reduction per query. And this is running the large scale analytics in a single cloud in EA. They're benchmarking their Presto workloads talking to S3 and using Alluxio as a caching layer. They see 2 to 4 times a average performance improvement in running the benchmark, and 7x key query speed up, and with 50% cost saving without copying the data again. And this is because they have the data locality, and this is less from having the virtualization, but more like on the efficiency side, just having the hot and repeatedly use the data closer to the application. So I want to share a little bit what we see the journey. Typically, we see a lot in our community. Initially, they have this HDFS cluster, and they're adding this object storage. So they want to have a unification across different data stacks. And then they want to enable running analytics over this object store. So in this case, Alluxio can be a layer to bring data closer to their applications and speed up their, for example, Presto training workloads or Spark jobs. And next, they want to enable the hybrid cloud choices. They want to, without giving up their applications, their existing infrastructure in the on-premise data warehouse. I also want to run my workloads in the cloud, especially when I have a lot of jobs suddenly submitted, and I don't have the capacity to sustain all these jobs. And how can we enable some, for example, using some resource from cloud to solve these issues. And this is what we call the hybrid cloud, and burst these workloads to the cloud. And we can, so this is the next step they are saying. And after going to the cloud, or partly going to the cloud, they also want to see how we can replicate the setup from AWS to Google Cloud or Microsoft Azure, then choose the right tool to use to run the jobs regardless of the cloud provider. This is a very typical journey we have seen in the past across our in our open source community, and they're talking to us like, how can you enable this journey? Like, for example, if you having this is an example. We have a HDFS. We have some like replacing there. Maybe this is a cloud and this is object store, and running this in the on-premise data warehouse, and then they go to one cloud provider, and then another cloud provider. And we're saying, okay, if you're having data challenges like this, why don't you just think about having this virtualization layer to help you solve this problem by having Alluxio sitting beneath the applications. Here is some other applications architecture overview, talking about how to enable hybrid data lake. But I don't want to go through the details. This is talking about how we implement this system. I just want to focus on a few interesting points. One is that we call unified data namespace. So essentially, you can we're providing. You can think we're providing a logical namespace here in the middle, and you can mount the physical and persistent storage into this logical namespace. This is what we're doing, and this analogy is really running a Linux box. You have this VFS layer, virtual file system layer. As long as for example, your hardware hard disk provider, they implement a driver. The driver is compatible with the VFS, or the driver is part of VFS. Then you can use your new hard disk without really knowing, just like using any other folder or device in your Linux. So it's exactly the same analogy, but moving this analogy to a different scope, like for file system, for distributed file system, storage system, cloud provider, public cloud service. And you can mount different cloud and different services into this logical file system, just like you put a hard disk to a Linux box. So that's, from user's perspective, that's what you see. And based on this logical layer, you can just add more policies. This is a more advanced, where this is some open source, a lot of open source users giving us ideas. Hey, I have already got this logical layer. How about having a more advanced data policy here? For example, you can migrating the data from one device to another. In this case, like from one service to another service, a cheaper service because the data is less used. But you keep the logical file path the same without asking the application to change the name. So yeah, this is a good idea. So we implement this called data policy engine. So this can provide you the consistent logical file system view without exposing the details, how we really store the data in different services. So I want to switch the gear a little bit. So essentially, in the past 2 years, we have seen a surge in the application, in applying this technology for machine learning and AI workloads. So I want to talk about a little bit about it. So what is the I/O challenges in machine learning and deep learning, especially deep learning phase? One is we see the training data is getting bigger, and also consists of massive amounts of small files, billions, like as I mentioned, billions of 100 kilobytes photos. That's the scale we're talking about. And the size of the training data keeps growing. Used to be the case that training data is likely to fit your own hard disk. So in a lot of tutorials, you're running how to do a deep learning training. It says, copy this data set to your local disk so you can run this efficiently. But in production, especially for many giants, they have a lot of data. So that is definitely not feasible. They have to provide a way to access data not only served by a single node. That's going to be the bottleneck. And also the training jobs are highly concurrent thanks to the latest advance in hardware, especially like a GPUs. And you can easily get thousands of different concurrent threads accessing the data to keep your GPU utilized. And that requires a very different design to serve this type of workloads. So we are talking about like how, for example, if you're running a TensorFlow and you're accessing the data from object store, and we're just what we're talking about is we see a lot of our open source users are using us as the distributed caching layer for your deep learning, but exposing the data from the POSIX API to the TensorFlow or different other instances, so they can access the data just similar like you're accessing the data from your own laptop local folder. So in that case, you don't need to fetch data and all the data on the cache miss, and this is a data fetch will be automated, and you don't need to copy the data before the use, and you don't need to clean up the data after use. So everything is automated. And in this way, we can enable direct access to data and low latency, consistent performance, and high GPU utilization. And this is how one of our open source users called Momo is running thousands of the Alluxio nodes across their cluster, and they want to speed up their data access for the training to access data on HDFS and Ceph. And they have, in this case, they have 2 billion small files, and they reduce the metadata data interaction with Ceph by, I think we have more data shown in this link. Yeah, so that's the end of my talk, and I want to keep this actually short and in a relatively high level, so I have more time to engage, and I have more slides to detailize my statement. Let's go back to the Q&A. So I see it's also from Case. Do all Alluxio powered instances see the same namespace? Yes, they see the same namespace. How is visibility controlled? For example, maybe some on-prem data is hidden from the cloud. So you can provide, like for example, you can just mount a directory in your on-premise data warehouse to this namespace without exposing other parts. So this is part one, and part two is we support Unix-like security permission authentication, this type of like a access control. So even you're in the same namespace, it doesn't mean you can access that, right? You have to get a permission. With my user, with my group, I get the permission bits to read or write in that logical namespace. So that's all controlled by us. Okay. Once the file is cached to a node by Alluxio, what is the latency impact? If I have a latency sensitive workloads, especially for small file, is Alluxio still appropriate? It's all relative. I think it's all relative. If you have a data, for example, especially in the cloud environment, or you're accessing the data from a remote data warehouse, then that is going to be definitely Alluxio can dramatically, like we see 10 times, 20 times speeding up the IO access. If you're talking about, oh, this is on my own already the same machine running this application, so accessing the data from the same machine, data stored in the same machine, I don't see the point actually in that case to use Alluxio to speed it up. It's more like in the distributed system, in the setting of running a distributed system. That's where you are having this IO issue, especially accessing data from different locations. Yeah, but if you have everything already co-located, having Alluxio is not my recommendation. And we have seen, and also it's more like a throughput bound, I would say. It's not a latency. Typically, it's a throughput. for a single node, if you use SSD or use memory as the storage media for Alluxio, allocated to Alluxio, to this layer, we have seen gigabytes, at least on the per second, gigabytes throughput per second that can be achieved easily.